Hello. In this video, I will continue to talk about binomial expansion. I'm going to actually introduce an idea about the binomial expansion, which would require some in which I have to make use of some ideas that I would only talk about much later under a topic called Maclaurin's series. Okay, so this is something I'll talk about much later, but it seems like this is a good place to mention it, to take a sneak preview of this later topic, because it is one of the things that one of the useful things about the binomial expansion that we should know. Okay, to start off with, it has to do with the idea that I want to talk about has to do with the power. If you remember, the power has to be a whole number. Of course, I've been talking about expansion and multiplying a few brackets together. Like, for example, when the power is 10, it means that I have to multiply 10 of these brackets, 10 of these 1 plus x factors together. And this also means that I would have a fixed number of terms in the expansion. So for example, let me just let's just remind ourselves by writing out the two simpler examples that I've seen. When this was 1 plus x squared, I had 1 plus 2x plus x squared, and this means I have 3 terms here. Okay, so when the power is 2, this expansion stops at x squared, and when I have 1 plus x cubed, it's 1 plus 3x plus 3x squared plus x cubed. So this expansion stops at x cubed. So it's quite easy to know when it stops. When it's squared, it stops at x squared. When it's cubed, it stops at x cubed. So the power of x where it stops is the same as the power of this factor of this binomial. So from this pattern, we can easily guess that if the power is 10, then this should stop at x to the power of 10. And if the power is n, then it should stop at x to the power of n. So that seems clear enough. Okay, now comes the idea that I want to introduce. The idea is that even if this power is not a whole number, even if the power is not a whole number, we can still apply this formula, this binomial expansion formula. It will still work. So what do I mean by saying that the power is not a whole number? Okay. Let me clear this part out. Right. Let me write out an example. Suppose that the power is 1 plus x to the power of. Suppose that the binomial is 1 plus x to the power of half. Okay, suppose that the power is half. The half is not a whole number. Okay, we know that 1 plus x squared means 1 plus x times 1 plus x. Okay, so that's fine. But we can't think of power of half like this. And if you remember, we had it was from this kind of expression that I explained how we obtained this general formula for the binomial expansion. But if the power is not a whole number, is not a whole number, this is not going to work, right? But the surprising thing is, as I've said in a later topic called Maclaurin series, I will show that even if the power is a fraction, and even if it's negative, okay, the same formula can be used. The same formula can be used. So in a way, if it helps, all right, if it helps you to think about why we can use this, you can maybe just think that the reason that if you like, you can think that it is kind of just a coincidence. All right, it is like a coincidence that we can still use the same formula when the power is not a whole number. Okay, the actual formula has to be derived using a different method to what I described in the last video for this binomial expansion. It has to describe using the method of the Maclaurin series, as I mentioned. But it just so happens that the formula ends up looking exactly the same. So that's one way we can think about it if you find it confusing. So that means that there isn't a direct logical connection between using the formula for a fractional power. Okay, we are taking a jump here into some future topic. The results of some and bringing the results of some future topic into here, and we're doing it here because it just so happens that the same formula can be used. So let's try using it now. So assuming that I can actually use the same binomial expansion formula for this fractional power, let's see what the expansion looks like. 1 plus, okay, since n is half now, nx would be half x. And then this, okay, I just need to substitute half into the n here and here, and I get half and a half minus 1 over 2 factorial. I have x squared there, and so on. And let me just simplify that. Get 1 plus half x. Okay, let's see. I have a half minus 1 here. That's actually minus half. So I get a minus sign now. A half times a minus half divided by 2, that would be 1 over 8. x squared plus dot dot dot. Now, while using this same formula for the fractional power, there are two things we need to take notes of. One thing, okay, take notes of this. If we come back to this previous example where the power is 10, recall that the series stops at x to the power of 10. Okay, the first term has 0 power of x, second term has power of 1, and so on. So x to the power of 10 is actually the 11th term. It's actually the 11th term. Okay, so if the power is 10, we have 11 terms. If the power is n, okay, by this pattern, we could see that it will stop at x to the power of n, which is the n plus 1th term, the term number n plus 1. Okay, so that's clear enough. But what about a fractional power? Where does it stop? Dot 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 until where? We can't exactly have a half plus 1 term, and clearly I've already written out more terms than 1.5. Well, the answer is that it does not stop. Okay, it goes on forever. The series goes on forever. So there would be an infinite number of terms. It just keeps going. Okay. Now that if you're seeing this for the first time, it would feel really strange. And over the next few videos, I'll talk more about such infinite series. And one of the question that we need to get think about is, if I have an infinite series, then when I add up an infinite number of terms, alright, if I keep adding numbers forever, won't the answer just get bigger and bigger? Okay, so that's one of the questions we have to look at. But for now, let's assume that everything is going to be okay, and that I'm going to get an answer which is reasonable, which I'll show in a moment. So the next thing that we need to note, let me just mention the next thing before we go on, is that the value of x has to be less than 1. Okay. Okay, I'll write it out this way. The magnitude of x, or the modulus of x, has to be less than 1. Now, if you have not seen this symbol before with the two lines, it just means, if you like, I'll just call it the numerical value for now. And by numerical value, that means that if it's a negative number, we drop the minus sign. So if it's minus 2, then this just means 2. If it's 3, if x is 3, then this still means 3. So numerical value means we just drop the minus sign and look at the numerical value. So for this series to work with the fractional power, the numerical value of x has to be less than 1. And the reason is that if it is more than 1, then when we start adding up all these terms, the terms would actually get bigger and bigger. And then we won't get a definite answer in the end. But if x is less than 1, you might be familiar with this already. For example, if x is half, then if x is half, x squared is 1/4, x cubed is 1/8. So you can imagine that the terms just get smaller and smaller. So when you keep adding more and more terms, alright, it is just possible that the answer does not actually keep getting bigger and bigger. We'll see more of this afterwards in a later video. But for now, let me just finish up this example by looking at say what happens when x has a certain value. So as an example, let's say x is equal to 0.01. So if x is actually equal to 0.01, let me try and calculate what this answer is using just these three terms. If I put x equal to 0.01 into here, and I add this up using a calculator, which I did, the answer I got is 1.0049875. Okay, so this is what I got when I substitute x equals to 0.01 into here. This is what I got by adding up those three terms. Okay, and I also did something else. I also put x equal to 0.1 into there and use my calculator to evaluate the square roots directly. So in other words, when I put this into there, I get let's see, I get 1.01, right? 1 plus 0.01 is 1.01 to the power of half, which is a square root. Right? To the power of half. And when I put this into my calculator, what I got was 1.0049876. So this is the exact value, or the accurate value, which I got by evaluating the square roots, the power of half, directly using my calculator. And this is the value that I got by adding up the first few terms, just the first three terms in this series, this binomial series. Now, if you compare this with this, you see that they are actually very, very close. See how many decimal places I've written now? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. I've written down 7 decimal places, or 8 significant figures, including the 1. And they all agree except for the last figure, which is 6 here and 5 here. All the other figures agree. So you can see that I get very good agreement between the two just by taking these three terms. Okay, and you might just imagine that it should be a lot easier to add these three terms, these three numbers, than to do a square root. I mean, you need a calculator to do a square root, right? But you can actually, if you want, you can actually just sit down with a pencil and paper and actually calculate these fractions and the 0.01 squared by hand and actually get this number in I don't know, maybe 10-15 minutes. So it's comparatively easier to do this calculation than to do this calculation. And what this means is that the binomial expansion actually gives us a way to calculate calculate accurate values, maybe approximate but still accurate values in a simple way. And this is actually the kind of technique that is implemented in some kinds of calculations in calculators and computers.